Or
I'd rather not get recorded if I can do it upstairs.
if you want to do it upstairs,
Guys, come on.
we'll do whatever you'd like.
When it comes for your turn. Yeah, I don't want
I told you, I'm gonna show up in like a suit, glasses on.
I could
Whenever
be
you're
the
ready,
green
you're good to
color.
go.
Okay, we're ready to go. So last time we were together, I ended the process talking about ratings for Windows. So there is an opportunity for you to pay attention to what you're purchasing should you get to the point of doing window replacement. But the question always comes up, okay, I can do a rating. What rating should I ask for? So this slide can give you some general ranges of things to be looking for in general. Obviously, this is a really generalized layout. It doesn't tell you all of the intricacies. Does the window face south? Does the window face north? So on a broad basis, if we're looking at a cold climate, typically we're looking at windows that have higher rather than lower R values, or alternately lower rather than higher U values, because we're interested in really preventing the amount of conductive heat exchange through the glass. It's the biggest factor involved when we're in a cold climate. By the same token, we're going to look for higher visible transmission and higher solar heat gain coefficients. When we go to the opposite end of the scale, when we're looking at hot climates, you still want fairly good resistance to conduction. But it doesn't become quite so critical, so it's harder to justify high R value windows. You can probably justify a triple glazed windows in a very cold climate. It's very difficult to justify triple glazed windows in a hot climate. We're also going to be looking for glazing that has a limitation on the amount of solar heat gain. When we're somewhere in the middle, well, those ratings should be somewhere in the middle. Things we don't want to forget is the spacer between the glass. It's worthwhile investing in warm edge spacers no matter what climate you find yourself in. And frames as well, you want to make sure that they're thermal broken, because those short circuits are going to cause you a problem no matter what location you're in. And finally, same situation with air leakage. Air leakage is going to cause you more problems in a cold climate, but there's not a really significant penalty for going to a window frame that has good performance in terms of air leakage in all climates. This is some references that you might find useful in going back to look at additional detail on windows. I'm going to switch gears now, but before I switch to another topic area, any questions or comments about windows and their impact on energy conservation and their use in retrofits? Okay, good. I will see if I can figure out how to move to the next thing. So how do I get back to the desktop, Perry? I guess I can just close out this PowerPoint.
Yeah, if you're wanting your
Oh, I can just minimize it. So now I
and
can
then
use.
it's on Firefox.
So I had a very simple, maybe even naive question about conductive heat loss or leak gain. So conductive heat loss or heat gain is basically passes only through solids, right?
No, that's not totally true, because all air-based situations is going to have some additional content. For instance, we're breathing atmospheric conditions here. We look through it, so it looks like there's nothing there, but is there something there?
Yeah.
Yeah, it's full of particles, it's full of moisture vapor, and all of those things add to the conduction that's possible. A vacuum, yes, does not have something to conduct heat flow through. But beyond a vacuum, there is always something. Now, what we're down to is, on a relative basis, how much? And on a relative basis, all of the gases are going to have less of a factor in terms of conduction, but automatically both gases and liquids add in the issue of convection. Because now we're going to move around more heat because of the movement of the fluid, either gas or liquid, rather than the amount that's being conducted through the material itself. So, good question. And it certainly applies in the case of windows, because what's between the glass does in fact have some factor involved. So far, I've concentrated on things that were involved with how do we improve the efficiency of the envelope of the building. There's obviously a whole bunch more, because we haven't nearly finished the semester yet. There's a lot of other topics to cover. So I thought this was a good opportunity to just bring up the subject of, well, how can we go about deciding what to attack? Now, if I'm in the business of making or selling heating and cooling equipment, I know what I'm going to attack, because I've sort of got my self-interest involved in the products that I am involved with. But if you're involved in the whole building view of the energy conservation, you might want to take a little bit different approach and say, well, you know, how can I begin to make educated choices, because one choice impacts another. And I wanted to remind you that the Advanced Energy Design Guides gives you some tools to be able to do that. This one, this table 2.1, I think is out of the 30% design guide, but there's something equivalent to it in the 50% design guide. I've put a couple of highlighted areas on here for no other reason than just to remind me of some things to mention as we go along. But just to look at this process, on the left-hand side, it's got a column full of goals. And if we look through that line, they're all fairly logical things. It actually starts out with things that are not actually the building necessarily itself. It's what goes on within the building. If I'm creating a situation that essentially builds demand for energy use in the building by the occupancy or the use of the building, we might be able to control something about that. And it may actually be a no-cost or a low-cost option. So they're good places to start. Reducing heat gain and loss to the building envelope, we've talked about. Reducing energy use through gain and loss in the ductwork is tied into the HVAC system. The next topic that we're going to talk about is the heating and cooling system. And as we look at this chart, the next column over is strategies. So, you know, if I decide that I'm going to attack one of these things, what ways can I go about attacking the process? And then a little bit more detail about each of those strategies. Some recommendations, and it references different parts of the design guide, and then actual how-tos. So, you know, if you think you're working in a specific area, you'll pick that area, look for strategies, go for more detail in the design guide, and finally specific information that might be some drawings and specific instructions within the design guide. So you can use this guide not as something that you study and you learn, but as a resource for future work. I don't think there's anybody that's likely to know every detail of every kind of strategy that's shown in the design guide. So the second piece of making decisions, we've also touched on a little bit, and that's this whole idea of climate. And what does climate do in terms of impact on decision making? I'm using the United States as an example. Every part of the world has similar things going on. This design guide is set up to help you in the United States. If you're elsewhere, you'll need to find some other types of resource to give you some information. What you're seeing on this screen is a map of the United States that's been broken down into essentially climate regions based mostly on temperature extremes. Is this a perfect source? It is not. You'll have to be looking at more detailed information when you get to a specific location. And I'll use some contrasts. For instance, if we were to look at locations in the southern part of the United States, the automatic assumption is that it's probably going to be someplace which is warm most of the time. That's certainly true of the area that's around Florida, southern part of Louisiana, across into Texas. We also expect those areas to be fairly humid, a lot of atmospheric moisture. If you move farther west, all of a sudden we change to a slightly different dynamic. Even though we're pretty far south, you're probably going to find high temperature extremes, but you might find temperature extremes in both directions. If you look at places like Arizona and New Mexico, you'll see you don't have to go very far north into those states to find extremes that now are beginning to look like cold areas. We've now looked at locations that have a very different dynamic. And the dynamic there may also have to do with time of day in addition to season. For instance, if you were to go to Arizona or New Mexico, you might find temperatures during the day which are in the 70-degree range, but at night would be in the 40-degree range, even in the middle of the summer. So your strategies will probably be different there than if you were in Indiana, for instance, where you're not likely to see those temperatures extremes in the summer. You're going to find consistent heat. Windows are a great example of something that you might do differently in those locations, because all of a sudden, capturing radiant energy during the day in a climate that doesn't have many clouds might be a really good strategy. So the design guide gives you guidance on climate, but remember that the guidance on climate is pretty limited. It isn't one thing fits all when you get into these territories. The second resource that is out there is, if we looked at that Table 2.1, Table 2.1 had a whole series of approaches and strategies. If you look at that table, some people just sort of get frozen by it. Well, there's too many choices. How do I decide? And how do I decide what thing to work on first? How do I know if I spend all of my time and energy on Windows that that's really going to have a significant impact on the energy use of the structure? These two graphs are out of the 50% design guide. And what they're really designed to do is to give you a better sense for where does the energy get used in the building, so that you can now make your choices based on where you might get the biggest impact. So if we look at this first graph, across the bottom there's a listing of various climate locations. Here it's actually looking at cities, so now you can get a much better idea of specifically how things operate. And you can also get some sense for differences. For instance, if you look at Chicago and Denver, they're both in Zone 5, but you'll see there is some differential in where the energy use takes place, even though they're in similar climate zones. And each one of these bars now is providing some evidence of where the energy use takes place. So if we go down to the far left-hand side, we're dealing with mostly a warm climate. Where's the biggest source of energy use in a light commercial building, typically? In the Miami area. It's the light blue bar. It's cooling. That's fairly logical. And it's something that we would probably make the assumption about. Once we get in the central parts of the country, now there's some other things that begin to pop out. And this is something that I think when I first started in this process was a surprise to me. If you look at the bottom of all of those bars, there's a pretty big line that's consistent across climates. It's exterior lighting. We don't usually associate exterior lighting to the building itself, but in terms of the overall energy use, it's in almost every case at least 20% of the use. So that lighting component is a big one. Yes?
Interior lighting, I guess.
Oh, it's interior lighting, excuse me. Exterior lighting is a smaller component that's just above it, but is still a major piece. So if you take that interior lighting and that exterior lighting and you add them together, it makes up the biggest component of energy use in light commercial buildings in every case except Alaska. So if I were to ask you, if you were going to go to a light commercial building and attack the process of energy use, what would be the best place to attack it first? It would be lighting. Now, what I don't know is how much of these graphs are actually including the impact on the interior environment when you include the lighting. For instance, in Miami, the interior lighting use is going to impact the cooling use as well. Because as we light the interior, we're also heating the interior with those lights. It becomes an internal load that's that much more that we have to cool. The second graph is an indication of the relative impact of making some change as part of a strategy to move things forward. And on the far left, you'll see a graph that essentially creates a scenario for a building that's a baseline, something for us to compare to. As we move to the right, you can begin to see some cumulative energy savings by taking some step. And in this first step, looks like heating is the things that has made the change. In the second step, and what took that heating change, it was changes in the envelope. About a 6% change. Next step, they're suggesting making a change in windows. And we've gone an additional 2% step. Adding exterior shading, another 1%. Then we get to this interior lights, and look at the size of the change when we start looking at that movement from interior lights. So this scale can begin to give you some relative idea on the importance to change. The last graph said interior lighting looked like something that you really ought to attack. This one sort of follows up and says, yes, lighting is an important consideration in making that change. And when we start looking at interior lighting, you can't really separate it from daylighting, because daylighting, if we allow light from the exterior to provide the necessary light in the building, obviously we're going to decrease the use of internal lighting and the internal lighting's impact on loads. So the next place we see a big impact is down here, HVAC and the size of the impact of that change. And on that basis, the next subject I want to cover is HVAC. Questions on strategy or an approach to strategy?
I think HVAC is something that really needs improvement as of now, because definitely what happens is, like, for example, if somebody's comfortable at a certain temperature, it's not necessary that other person close by are, not comfortable at a certain temperature, the same temperature. So there is a lot of human aspect to the temperature, and when there is a temperature differential, there is always more energy usage.
That point is actually well taken. We don't spend a lot of time talking in this class about the human impact, but it is something that you have to sort of include in every thought process. One of the things that I'll actually talk about in this HVAC process is control systems. And control systems tie right into that comment about how do occupants impact the process. If I let everyone have control of the heating and cooling system in a building, what ends up happening? One person turns the thermostat up, the next person comes along, they're hot, they turn the thermostat down. Next person comes along, they're not comfortable either, they turn the thermostat down some more. And we actually end up creating some very strange things going on in the heating and cooling system, especially when we get into a system that is complicated. And you'll see, even in light commercial buildings, that those systems do get quite complicated because often they are providing both heating and cooling at the same time to be able to satisfy the occupant's demand. So this issue of occupant comfort is a really big one. And you should have it in the back of your mind. As technologists, it's harder for us to say, these are the rules. In a lot of these cases, I'm giving you numbers or some kind of guidelines. With occupants, it isn't so easy. So I think the first place to start, since my major goal here is to talk about light commercial buildings with a little bit of, addition for big buildings and residential buildings, is to make sure that everybody's comfortable with typical heating and cooling systems in a light commercial building. There are two big categories of equipment that are commonly found in light commercial buildings. The first one we usually call a package unit. The name really is pretty indicative of what it is. In that package is everything you need. Ventilation is there, heating system is there, cooling system is there. Usually the entire process is controlled all in one package. These are very frequently mounted on the roof of buildings. Light commercial buildings very commonly have flat roofs, and if you go to big buildings that they put a sloped roof on, often if you go to the back of the building, they put a notch in that sloped roof to be able to put these package units and hide them on the back side. They're available in just about any kind of energy source you want. You can get electric ones, you can get gas ones. The advantage to them is they're simple to install. You set them in place and all of the pieces are there immediately. The second type of system that you'll typically see is one which is actually split into two pieces. One is located typically inside the building. We usually call that the air handler unit. That's the piece that actually moves the heated or cooled air or water around the building. And on the outside is a unit that's designed to take the waste heat during the cooling process and dump it into the atmosphere. These units do not have ventilation included, so there needs to be some additional control systems or some additional ducting or piping to move air in and out of the building. If we were to look at these commercial buildings in a schematic format, I could show you dozens and dozens of different variations, but this picture shows some things that are fairly typical. Commercial buildings will usually come in two broad categories in terms of heating and cooling. One of them is an air-cooled and heated building. This is probably the dominant one on small buildings. The bigger the building gets, the more likely you might see the other option, which is one that uses heated and cooled water. In some cases, it's steam rather than hot water to move the heat around the building. This picture is showing a situation where it's air that's used to move the heat in and around the building. So you essentially have a central location where there is a fan and a series of ducts that will carry air to where it's needed throughout the building, and then a series of ducts that bring the return air back to the air handler unit. What most people don't realize about commercial buildings is that the amount of heat that's needed is extremely variable throughout the building. And because it's so variable, it's difficult to supply just heat or just cool. There are some buildings that do have that situation. There are typically times of the year where comfort is hard to achieve because either the direction that part of the building faces, solar radiation adding to the heat gain, changes to the formula, the location within the building. I'm sure you've noticed if you go to the fourth floor, it's a lot different than if you're in the basement. So you need some different amounts of heating and cooling. To get around that, typically they supply both heating and cooling at the same time. In this particular case, it is using a control box at the specific location that has dampers which open and close and let in a certain amount of cool air or heat air to meet the demand that's called for by the thermostat. The important point about this heat and cool at the same time issue is things go wrong. Is there a possibility that you're providing heat and cool at the same time and they're working against each other? Absolutely, it happens. And in those situations, you have a wonderful retrofit opportunity. If you can just fix the control system, it might be in the damper control, it might be in the control that actually sends the signal to tell the damper to open or close. It could be just a matter of cleaning something. Maybe you have a damper that doesn't open or close like it's supposed to because through the years it has gotten to the point that it gets stuck in one location. All of those things can cause you to be heating and cooling at the same time.
When you say heating and cooling at the same, I don't know anything about HVAC systems really. I wish there was a moving diagram of this, but so how are the different thermostats? Say you have 20 different thermostats in a building, just something ridiculous like that. How are they all? If you turn something up or down, are you changing just the amount of heat that's coming in, or if there's heating and cooling going on?
Well, you ask a very, very good question, one in which we could spend the entire semester discussing, because the opportunities for variation are endless. So let's use some simple examples. In some cases, if heating is the most predominant need, and Knoy Hall is a pretty good example. During the winter, heating is the most predominant need. What they'll actually do is they will supply heat constantly. And then they will have a system that opens up a damper and allows cool air in to cool down the space if too much heat is supplied. Now, are there downsides to that system? Sure there are. There's situations when you may not have enough heat because you're supplying a constant amount. The system that is shown here takes a slightly different approach. It says we need to be able to control both heat and cool. So the thermostat is now located in a location that is someplace central to the control area. The simplest approach would be a single office. If I have a single office, I put the thermostat in there. I have a control box. It has a duct that comes from the heated supply side and a duct that comes from the cooled supplied side. If the office is cold, you close the cool side damper and you open the heat side damper. If the situation is where the office is hot, you close the heat side damper and you open the cool side damper. And you attempt to meet the set point that the thermostat calls for. Now, this is actually a great opportunity to talk about those situations where occupants really get in the way. So what if you have the occupant that is sitting at their desk and they are hot? So they turn the thermostat to a cooler temperature. All of a sudden, you're going to have cool air blowing into that space. And then they go, oh my God, I turned the thermostat too cool. And they go and they turn the thermostat back up. Now we have just the opposite thing going on. And we always have something that we call overshoot. You set the thermostat may or may not shut off just at the temperature that you set. But at the very least, there's some delay. And what a lot of people forget is, if I take the thermostat and I turn it all the way up, will the office get any hotter than if I set it to the temperature I want it to be? It doesn't get hotter any faster. It's still going to take a while for the system to catch up. Well, in the meantime, we've turned the thermostat all the way up, and now it will wildly overshoot until the occupant, who may now have gone to a meeting and won't be back for 2 hours, comes back to a sweltering hot office and now has to turn it the other direction. And their automatic reaction is, I'll turn it all the way down, that'll cool it off faster. So you can easily see how the occupant is really making this system crazy.
Because you have to, in a residential area, thinking about like just turning the thermostat on and off. Let's say you leave and you don't want to have it on for a little bit. Is it, I had a friend saying, oh, it's better to leave it on, and perhaps that's because it doesn't have to use all this energy to get back to 68 degrees, for example, as opposed to just kind of like leaving it on at a constant temperature. Is it true that it would be?
The question of, do I use a setback or do I not use a setback, again, is not a simple one. The universal answer is, in most cases, there are benefits. But there are some examples where it does work against you. And let's move on to residential systems, because they're easier to understand. And I'm going to jump ahead to the electric systems. So on the right-hand side, I've got two kinds of electric systems. The one at the top is the simplest and least expensive system that you can find to heat a residence. You use electricity to heat up a wire, air moves across that hot wire, and you now have a warmer space. Now the challenge with that is it tends to be a very expensive way to heat because of the inefficiency of distribution of energy. How did we produce that electricity? We probably burned something. We may have burned coal, we might have burned natural gas, we might have burned fuel oil. That process of burning might be pretty efficient. Maybe we're even 90% efficient in that burning process. But now we send it over wires over miles and miles and miles, and we have some inefficiencies in how we distribute things. We have transformers and we have control systems, and we have to keep the system operating to make sure we meet the peak demands. And we lose efficiency. The amount of efficiency that we lose is amazing. We're dealing with end-use efficiency of the burning of that flame of something between 20 and 40%. So we could have lost anywhere between 60 and 80% of the energy that was available in what we burned to create the energy. That automatically makes this electric resistance heat an inefficient and expensive way to heat. So if we have no other option, if we must use electricity, how can we do something more efficiently? And we do that with the example on the lower side. We use a heat pump. A heat pump is the easiest, although not technically correct explanation, is the reverse of an air conditioner. An air conditioner, we are moving heat through a refrigerant cycle from the inside of a structure and expelling it on the exterior of the structure. With a heat pump, we're removing heat from the outside air on the outside and moving it to the inside air. And what really is the big difference is the temperature differential between the two. Because with an air conditioner, how much temperature differential do we have? Maybe 15 or 20 degrees. If we're moving from the outside to the inside, how much temperature differential do we have? It could be 60 or 70 degrees difference in temperature. Because it gets to be a more complicated and difficult process, and to make matters worse, we have to make it so that that system works both directions with both of those different temperature differentials. But the fact remains, even though we think it's cold outside in the winter, there is still some heat in the air that can be harvested by these systems, and we are able to move the heat inside. These are more efficient systems. We can do things maybe 2 to 3 times more efficiently in terms of heating using a heat pump as opposed to electric resistance heat. So it is a common choice for heating, especially in the middle part of the United States.
When you say it's more expensive, do you mean just upfront it's more expensive? Does it cost less after?
The electric resistance heat is very inexpensive initially, very cheap to put in the equipment, but very expensive to operate. A heat pump, on the other hand, is more expensive to put in initially, but much less expensive to operate long term. So now we get back to this question of controls. Do I have the ability to save on my energy use if I set back the temperature at night? So I go to bed at night, at 10 o'clock at night, I turn the temperature back 8 degrees. And then when I get up in the morning at 6 or 7 o'clock, I want to make sure that it's now 70 degrees inside. Fairly easy control process to use. And if I had a furnace that burned natural gas, would definitely save energy. Because I'm not heating this interior space, my temperature differential is smaller, the amount of heat loss of the structure is reduced, I have less need for input of outside energy to keep the structure warm. But with a heat pump, the dynamics change a little bit. Because what's the heat pump doing? It's removing heat from the outside air. Is there more heat in the outside air at 1 o'clock in the morning or at 6 o'clock in the morning? If you look at the temperature in at least the part of the country that we're in now, the temperature gradually drops overnight. So your lowest outside temperature occurs when? Right in the morning, just before the sun comes up. So if you're asking the heat pump to pull heat out of the air at the point when the temperature is the coldest on the outside, then you may not get quite the savings that you were hoping for. Will it be some savings? Probably. Will it be as much as you'd like? Maybe not. Now, is that a reason to abandon this process? No, because we have great electronics control folks, and they realize that this problem exists. So they have thermostats that actually track the history of outside and inside temperatures over the most recent past, and it adjusts the heat up process so that the heating doesn't take place right at the coldest point in the day. There's probably still some penalty because it's a heat pump, but the control system makes it so that the penalty is much less. The decision now is, do I buy the $50 thermostat, which just automatically turns down and turns up the temperature, or do I buy the $115 thermostat that has an outdoor sensor, and it also has a little microprocessor, and it looks at the history and changes the control process? So we also have other heating systems shown in this slide in the residential setting. The one on the left-hand side is pretty much the most desirable system if appropriate fuel sources are available. They're forced air systems that utilize a source of heat to burn. 100 years ago, that would have been coal. We don't use coal anymore direct at a residence, but we certainly might use natural gas or fuel oil. Because we're now burning that fossil fuel right at the site, we have a pretty efficient delivery process. Natural gas comes to us at the resident at 100% of its value. It hasn't been degraded as it passed through the pipes. Fuel oil, same situation. Whether it arrives with a pipe or whether it arrives in a truck, it's got 100% of its potential. So what we're up against is how efficiently does the furnace itself capture the heat from the burning and passes it to the air. We now use air to distribute the warmth or cooling through the residence through an air handler unit. There are parts of the country where air conditioning is called for less frequently, and an efficient system for those locations is often something we would call a hydronic heating system. Basically, it's using water as the heat transfer mechanism. So we use pumps and hot water to move the heat from the source of energy to where the heat is demanded. There are some advantages from a comfort standpoint with hydronic heating, especially if we can heat a large surface area. The top picture is actually a picture of piping that's put in a floor system before the finished flooring is put in place. The temperature of the water that passes through here is just a little bit higher than the indoor air temperature, but you feel nice and warm because the floor is warm like your body temperature. And that radiation up into the air now heats the air, but you may not have to have as high a temperature setting because that nice warm surface that is close to you gives you the comfort. In older systems, we commonly would see radiators that were close to windows. Why did we put them close to the windows? Well, the window was cold. If we could put a hot surface close to that cold surface, it gave us the illusion of uniformity there, and it was very helpful. The downside to hydronic systems is not that they are something lesser in terms of their performance, but they require a double installation of equipment, because in most locations, air conditioning is still desired. So you still have to put in a series of ductwork. You still have to have an air handler unit to blow the air around, but you're not using that portion of the system for heating. So you essentially have two or a duplicate distribution system, one for water, one for air. Yes, Sam, you have a question?
So in kind of colder months, these type of systems, you actually have kind of a lower cost since let's say in like the floor heating system, your like Mass Effect heat, I guess, conservation, I guess, is high because it's just heating this large surface area and it's keeping everything at a relative temperature. You're not constantly heating a space over and over and over again. Is that like in comparison to like a heat pump or whatever situation?
There are some potentials for advantage with the hydronic systems because of that mass effect. There are a lot of ways to kill that advantage.
Okay.
One of them is, what do the occupants do?
Yeah.
This is a case where, remember I mentioned temperature swings, it's especially troublesome. How long does it take for that floor slab with the hydronic coils in it to warm up and cool down? It takes a long time. So reaction time is very slow compared to forced air. I mean, you turn on a forced air system and you feel heat coming out of the ductwork right away. On the other hand, with hydronic systems, it's going to be not a minute or two, it's going to be tens of minutes and maybe even an hour before you even recognize a difference in a lot of these systems in the interior space. So you can actually have the occupants get in the way of efficiencies. The second place you can run into inefficiencies, and the reason why blanket comparisons don't work is, in a lot of cases, these are done on buildings that are on a slab on grade, and often a lot of the heat energy is lost to the ground because the floor slab and the ground aren't isolated appropriately. So, you know, this blanket statement that this is a better way to go is never a good choice. But it does have the potential, especially if you compare it to a system where it's a forced air system and all the ductwork is in the attic and uninsulated. So, you know, now you've killed the efficiency of the forced air system.
Is there any chance of leakage in the hydronic system, like especially when you put them in the slab?
So the question of leakage in the hydronic system is an appropriate one. Does a leak ever occur? Absolutely. Does it occur less often now than it used to be? Yes. And there's a couple of reasons why that's the case. One of them is you really can't tell too much in this picture because it's rather small, but in essence, all of those pipes are one continuous pipe. There are no joints that are put in the enclosed space, and it's usually those joints or junctions that are a problem. You know, if we look at history past, we didn't have, other than some very expensive materials, available to us to make this continuous. So we would end up with a lot of different kinds of connections, and those connections can end up being a problem. The second factor is just that the cross-linked polyethylene piping that we tend to use now also has much better durability than some things that we've had in the past. Now, are there some downsides? Sure. What might we have used in the past? We probably would have used a metal pipe. The metal pipe had a better heat exchange between the water in the pipe and the slab. The downside is the slab itself might actually attack the metal and cause it to degrade over time. Here we don't have quite as good a heat exchange, but we also don't get that breakdown that we had in the older systems. Now, it actually does bring up an interesting point, and that is, if you are looking at this kind of system as a retrofit, how many options do you have? Not very many, because you can't really do a retrofit unless you intend to be replacing floor systems anyway. It's a real challenge. Even if you're on a wood floor, and you can do a hydronic system on a wood floor, you still are in a situation where you have to completely replace what was there before and or add to the top of the existing system. And when you add to the top, you may be adding 1.5 inches or so, and now your doors don't fit and all of the trim doesn't work anymore. A lot of repercussions. With the forced air system, a lot more flexibility in terms of replacement, especially if you have access to the ductwork. So the kinds of problems that we deal with heating and cooling systems, and we've actually mentioned a number of them already, is obviously we've got this issue of what's the efficiency of the system. We've got a really big issue with equipment sizing. The comment before about what do occupants do, that really does impact the sizing of the system. The sizing of the system impacts system efficiency. And I'll talk more about that in detail. Most people don't realize the impact of having too large a heating system on the efficiency of operation. When we're dealing with retrofits, we've got this whole idea of what's worn out. Does a piece of equipment that has 90% efficiency when it's installed have 90% efficiency 10 years later? The likelihood is next to zero. And then we've got this whole issue of moisture control. It's the reason why we call cooling systems air conditioners most of the time, because we're conditioning the air in more ways than just cool. We're also dealing with removal of particles and changing humidity levels. Then we've got this whole issue of, since the bulk of the systems that we see in the United States use some form of air distribution, we're moving heat around through the movement of air. All of those issues of pressure balance that we started the semester with begin to pop up. And having pressure balances that are inappropriate create lots of inefficiencies. And they're a great potential for retrofit. And then the last one is, how do we move the air around? Well, we move them around with ducts. Ducts have their own special sort of energy issue. So if we start the list by talking about efficiency, part of understanding efficiency is really just understanding the language that is used in equipment. And to some degree, this has been a moving target, because as things change and as equipment has become more efficient, some new terminology has become available, as has the ranges. But what's on this slide is just some indication of some ranges of potential for high efficiency equipment. So if we were to look at residential heating equipment and we started looking at a natural gas furnace, the natural gas furnace has the potential to be on the order of 94 to 98% efficient. Basically what that's saying is it's based on the fuel energy input. So as the natural gas enters the furnace, how much heat potential is there in that natural gas compared to how much actually ends up in the air when it leaves the furnace. So it's just talking about the equipment itself, what's going on there. So you can see we do a pretty good job of squeezing energy out of natural gas. It's really only rated based on the natural gas utilization. We have to remember there are other energy uses involved here because we use an electric motor to move that air around. And that's another big place for efficiency gains. And we'll talk more about fans and fan advantages a little bit later. If we only have the choice of electricity as our energy source, heat pump's going to be the most efficient choice. And in this particular case, the ratings that exist are a little bit less clear, because this is a really complicated situation. Unlike the gas furnace, which essentially operates in the same environment all the time, a heat pump operates in a different environment every single day. Is it sunny outside? Is it cold outside? What's the temperature? How much is the differential in temperature between the inside and the outside? With the heat pump, we have a really, really big impact in that the colder it gets, the less heat there is available. So if we're operating in a condition where it operates most of the time at 32 degrees or less, it's not a very efficient system. By the time you get down close to zero, there's not much heat there at all to squeeze out of that outside air. So here we have a much more complicated, and I'm not going to attempt to explain it, much more complicated rating called a heating season performance factor. The higher the number, the better the performance. Typically, if we're looking at something that's in the high 7s to 9 range, you've got a heat pump that's operating about as well as you can do right now. We've mentioned in the past some rating systems. In the US, the Energy Star system has ratings for heating and cooling systems, and to be able to use the Energy Star logo, you have to have at least a minimum of an 8. So that'll give you some indication of what to look for in a heating season performance factor. When we look at air conditioners, we have something that's very similar. And here's one of those places where the rating name has changed fairly recently. We used to just use something that was called the energy efficiency ratio. It was much more equipment-based and it didn't think much about what are the seasonal factors. What's the temperature differential? Because air conditioners are the same situation. If it's hotter outside, it's harder to dump heat into that air than if it's cooler outside. So if our temperature differential is small, we have more efficiency than if the temperature differential is big. The seasonal energy efficiency rating attempts to include those seasonal changes. For an efficient system, you typically will be looking at something between 14 and 20. The higher the number, the better seasonal efficiency that might exist. In the case of Energy Star, they use 14 as the cutoff point. There are some other things that you can look for that are specific that help this process, and this applies in both the heat pump and in the air conditioner situation, and that is the compressor, the thing that works that refrigerant cycle to move heat from place to place, has difficulty operating at a lot of different levels. So if you're asking it to move a lot of heat, and you have a system that's designed for supplying a lot of heat, it's typically operating pretty efficiently at that rate. But if you take that same system that's designed to move a lot of heat, but the demand is very small, it doesn't operate nearly as efficiently. So the current trend is to create compressors that operate at multiple speeds so that they're not operating at full capacity when partial capacity is all that's required. So those are choices. Now obviously when we look at all of these changes, if you want more efficiency, it costs more up front. And part of the decision-making process is how much do we spend? Is it worth the trouble? When we start looking at commercial HVAC systems, it's harder to be specific about things to look for because there is so much variability. And there's another impact that's involved here. The consumer and support from the federal government have been very strong in terms of creating more efficient residential heating and cooling systems. Businesses, on the other hand, just pay the bill and move on. And there has been very little emphasis in light commercial buildings on energy efficiency in heating and cooling equipment. So as we start to look at what you can do there, opportunities are great, but supply of equipment is very limited. And I just use an example. We showed that cooling is a big factor in light commercial buildings. So paying attention to cooling is pretty important. If we go back to those rooftop all-in-one units, what do you think the highest seasonal energy efficiency rating you can find on those units might be? About 10. There are a few extraordinary ones out there that get up close to the 14 level, but you're not going to see much that goes over 14. So I told you you had to be over 14 on the residential level. It's a challenge even to find systems at that level that service the commercial market. Now there is some movement in that direction. There are some companies that are working that way, and the federal government is actually providing some research funding to companies to improve their product lines. But it's a challenge if you're looking at a retrofit situation to really look for high efficiency equipment. There are some places that you can look in commercial situations that don't require a complete replacement. And that always is a problem. In a residential setting, if you're doing a retrofit after 20 years, the heating and cooling system is probably in a situation where it's easy to replace. The first cost isn't that high, and the systems are reaching the end of their life expectancy anyway. Commercial buildings aren't quite so excited about replacing equipment because the investments are large. Instead of $4,000 or $5,000 investment, they're talking about $40,000 or $50,000 investment per rooftop unit, and they may have 6 of them. So they're not going to get real excited about replacing everything. But you may have the ability to go back in and say, okay, let's just increase motor efficiency. We can do this as a retrofit within the equipment without spending $40,000 a unit. Maybe we can spend $1,000 a unit to increase motor efficiency. Maybe you can deal with the fans themselves. Is there something about the fan that moves the air that could be made more efficiency? Something about blade design or something about bearings that are now worn. If we're dealing with a hydronic system, here now you're going to be looking at pumps. Motor efficiency has improved dramatically in the last 20 years. Big changes in motor efficiency. So if you have large motors, those are often places that you're going to want to attack. I can't give you a lot of generalizations because there's such a great deal of variety, but those are places where you may very well want to hire the consultant who understands those issues and look at them as a possibility. This is something I just want to show you, not necessarily spend a lot of time on, but to let you know that this resource exists. This is something that has been created through the U.S. Department of Energy in one of their national research laboratories. There are a number of research laboratories in different regions of the country that deal with this issue of energy efficiency. There's one in Golden, Colorado. There's one, this one's in the Pacific Northwest. The one that services us is in Oak Ridge, Tennessee. And they have a lot of innovations that they have worked on, both from a strictly academic standpoint, like this one. This is basically designed to give you a comparison of what you could gain if you changed your rooftop equipment. And it's based on a number of assumptions. And you can go through each one of these blanks. And I would encourage you on your own time, go back to this slide, pull it up, play with the numbers. Clearly this is generalization. It doesn't fit your specific example, but it deals with advanced features of the equipment, the kind of building you're dealing with, your location, the schedule that you operate your building under, the capacity of the equipment, things that you might add to the equipment to make it more efficient, something we haven't talked about yet. Here they're using an economizer, and I'll talk about that in a little bit more detail. The electric rate that is involved in your particular location, how many units that you have, and even a discount rate for the financing if you choose to do financing or at least impute a cost of money on your investment. So you can see, is this investment worthwhile in the long run? When you do your final project in class, this is a resource for you. You can go back and use this as a source to say, if one of your suggestions, and I'm not saying replacement of a unit is necessarily something you will do, but if you chose to, this is a resource that you have to go back to that. On the subject of equipment sizing, it's really critical that work is done to properly size equipment. And let me, for those of you that haven't been involved in design for heating and cooling equipment for a residence or commercial building, some of the thought process that goes through the typical designer's mind and the contractor who may be the designer who actually does the installation. In their thought process, they have a couple of things that are just absolutely things they do not ever want to have happen. They don't want to get a phone call from their client that says, it's 95 degrees outside and I can't get my building cool. Why did you sell me something that wasn't sufficient? Or in the middle of the winter, it's 0 degrees out here. We can't heat our spaces more than 65 degrees. The process of designing is based on a lot of assumptions. We know that quality control in the installation of the equipment and in the building of the envelope isn't perfect. So when they do designs based on assumptions, and those assumptions may or may not be correct. So what do? Oh, this design says we need 100,000 BTU to heat this place at 0 degrees. It only gets below 0 degrees 5% of the time. Oh no, 5% of the time. That's not. Let's go to 99% of the time. If we go to 99% of the time, it says we need 110,000 BTUs of heat. And we know something's going to go wrong, so let's just bump it up to 150,000 BTUs, and we'll make sure that we never get this phone call. What's more, we'll actually make more money because it's a larger piece of equipment. That's what happens in real life. So now we put in this piece of heating or cooling equipment that's over-designed, and what happens? Well, the first things that happened to us is something we call short cycling. The equipment turns on. It takes a minute and a half to heat or cool the place. Then it takes another 2 hours before it calls for heating or cooling again. That short cycling process means that the equipment did not get an opportunity to ever operate at its most efficient. Because if you think about it, a furnace is going to be most efficient if it runs 24 hours a day, every day. Heat exchanger is always hot. Now, can we get it to operate that way? Sure, at 0 degrees or -10, that's what you want. But since we are always worried that that won't be enough, we overshoot it, so seldom does it ever get to that point. And if a client calls and says, it's 100 degrees outside, my air conditioner's running 24 hours a day, you should go, great, we did a really good job designing that system. But that's not the way your client often will think. So that's something that gets in the way. But now the other thing that happens is, if I give this really hot blast of air, and then I go back and wait 2 hours before I get another hot blast of air, I get sort of this internal cycle where the occupant's tempted to go and fiddle with the thermostat. So that adds inefficiency. The last thing that it does is, if I'm dealing with cooling, I also want it to do dehumidification. In almost every case, if I need to cool, I also want to wring some moisture out of the air. How much dehumidification will I get if I cool down in 2 or 3 minutes and then turn off the unit for an hour or two? Not much cooling takes place, not much dehumidification. The best dehumidification is if it runs 24 hours a day, every day. You can really bring a lot of moisture out of the interior air. So now we end up with elevated interior humidities. What do clients think about that? Well, I'm not as comfortable. It's too, they don't even know that there's a high moisture content in the air. They just know they don't feel comfortable, so they turn it to a cooler temperature. So we've added a really big inefficiency. Now, in our business of looking at retrofits, we're evil in terms of this process. Because what do we do first? We make the building more efficient so it calls for less heat and less cooling. By doing so, we automatically make the heating and cooling system over-designed if it wasn't before, and there's a really good chance that it was before. So now we have created a world where the heating and cooling system is inefficient. It's one of those situations that makes the argument that says, let's do one thing now and do another thing 5 years from now and do another thing 10 years from now as the energy prices escalate. Well, what thing do you do first? Well, if I do the heating and cooling system now, when I finally get around to making the envelope more efficient, what's the situation with the heating and cooling? If I do the envelope now and I don't do the heating and cooling, what have I had done to my sizing on my equipment? It's just one more of those many situations where we have complicated life because we need to be looking at this from a whole building standpoint. Questions on where we've been so far today? Okay, we'll pick this up same place next time. We all done, Perry?
Yeah.
Okay.